Greetings everyone, this is Mr. Mull. Today I'm going to do a podcast on deriving the kinematic equations of motion for an object that has constant acceleration. So the first thing I'm going to do is I'm going to start off by having you reflect upon the card on the hill lab. So the card on the hill lab, we got two different graphs. We got our position time graph, and it kind of had this parabolic, it was a parabolic function, and then we had our velocity time graph. Velocity versus time graph, and it turned out to be this linear graph. So what we did is we came up with some equations some equations to model the motion of those two graphs. This one turned out to be our final position was equal to 1/2 a over our change in time squared plus vi delta t plus xi. Okay, this was kind of like our first equation here. The next thing we did is we came up with an equation for the velocity versus time graph, and we found out that the final velocity was equal to the acceleration times the change in time plus my initial velocity. That was our vertical intercept. So this is another equation that we had. So looking at these two equations, we were able to rearrange this one. We were able to figure out what that term was, acceleration. Okay, that was also over here in this equation. These equations are nice, but in some of the problems that we're going to be looking at later on in the unit, if we don't know time, then these equations are pretty much useless for us. We can solve for time if we're given enough information, but if we don't know time and we have some series of unknowns, we're not going to be able to use these equations as effectively. So what I'm going to do is I'm going to show you today how we can derive an equation that describes this accelerated motion, but that doesn't give us the variable of time. So I'd like you to consider the following. Okay? So we're going to take the following. So I'm going to make a velocity versus time graph. And on my velocity versus time graph, okay, so here's my velocity, here's my time. I'm going to do one for a cart that went down a hill with an initial push. So I'm going to give it an initial velocity. Okay? So we're going to call this here vi, some initial velocity here, and we're going to call this up here some final velocity that it ended at. And we're going to say that this took some amount of time, and we'll call this delta t. So looking at this graph, velocity versus time graph, I want you to recall what the area under this curve, or the area of this velocity time graph, represents about my object's motion. Area under velocity versus time graph represents my displacement, delta x. But the thing is that because it's not constant velocity, I have this kind of weird funky trapezoid shape. So what we're going to do is we're going to divide it up into a square and a triangle so that we can find the area. So there's two parts. I have this little triangle, little base times height, and I have 1/2 base times height, and I have this little square, base times height. Okay, so what I'm going to do is I need to find the delta x of this whole area under the curve. So my delta x is going to be equal to 1/2 the base times the height of my triangle, so 1/2. Now the base of this triangle is going to be my delta t, and I'm going to actually put the height first. Okay, I'm going to put delta t the height first. So I have delta t is my my base, and then I'm going to put my height. The height is going to be this little region here. Okay, so looking at this region, mathematically I could say, well, that's the final velocity minus my initial velocity is going to give me that little chunk. Okay, so there's my area of my triangle, and then that's added to the area of that little square, the base times the height. And I'm just going to put my base times the height here. This is going to be delta t is my base, and my height is vi. Okay, so I'm going to go ahead and expand these terms. I'm going to multiply both sides by 1/2 delta t, and I'm going to rewrite this here. Delta x is equal to 1/2 delta t times vf minus 1/2 delta t times vi plus delta t vi. Next thing I want to do is I want to combine my like terms. So I see delta t vi, delta t vi. I'm going to combine those terms. I have minus 1/2 plus 1 gives me overall of 1/2. So delta x is equal to 1/2 delta t vf plus 1/2 delta t vi. Okay, so I've combined my like terms. Next thing I want to do is I'm going to factor out my like terms. And I'm going to factor out 1/2 delta t from both of these. So delta x is equal to 1/2 delta t. And that leaves me with vf plus vi. Okay, so this is the first part. Now, our problem of still having only equations with time is still kind of a problem, because this equation here also has time. So we have our three equations. I'm going to go ahead and underline this one. We have three equations so far. So looking at this one here, this one tells me a lot of information, but what variable does it not tell me out of all these possible variables? Looking at the one we just derived, final velocity, I don't find it here. No VF. I look at this equation here, VF equals A delta T, and this one doesn't tell me all the information. This one doesn't tell me anything about position. No delta X. Doesn't tell me anything about position. Looking at this one down here, it doesn't tell me anything about acceleration. So what I need is an equation that relates final velocity, delta X, and acceleration. I want an equation that relates all of those, so that we can have an equation that doesn't have time but relates all those other variables. So I'm going to do a little substitution. So we know that from the equation above, that my final velocity, Vf, is equal to A delta t plus Vi. So I'm going to rearrange this, and I'm going to get delta t by itself. So I subtract Vi from both sides, and I get, and then I divide both sides by A, and I'm going to get delta t is equal to Vf minus Vi over A. Okay, so this is my new delta t. So what I'm going to do is I'm going to take this and I'm going to plug it into this equation here and do a little substitution. So I'm going to plug that in, and I'm going to get, I'm going to rewrite what this is going to look like. Delta x is equal to 1/2, and I'm going to plug in that whole big term, Vf minus Vi, okay, all over A. So I'm doing a substitution here. And then I'm going to multiply that by Vf plus Vi. This looks like fun, because now we get to do a little FOIL. So I'm going to do the first, the outers, the inners, the last. When I do this, Vf minus Vf is Vf squared. And then these inner terms, minus Vi Vf, and the outer terms, plus Vi Vf, the inner and the outer terms are going to actually end up canceling each other out. So if you don't believe me, you can do the FOIL, but I go through this whole thing, I FOIL it out, and I'm going to get an answer of delta x is equal to 1/2. I have Vf squared minus Vi squared. And then those other terms are going to go away. So what I'm going to do is I'm going to try to rearrange this a little bit. I'm going to multiply 1/2, and that's all over A. Excuse me. It's all over A. So I'm going to rearrange this. I'm going to multiply both sides by 2A to get these things to cancel. I'm going to multiply this side by 2A. So now I have 2A delta x is equal to Vf squared minus Vi squared. And I'm going to get Vf squared by itself. I'm going to add Vi squared both sides. And I'm going to get a final equation of Vf squared is equal to Vi squared plus 2A delta x. This equation is an equation that relates final velocity, initial velocity, acceleration, and position. It does not have time. So if I don't know time, but I know these other things, 3 of these 4 other things, I can use this equation in more circumstances than I can with just the other 2 alone. So now we have 3 equations of motion, and I'm going to relate all 3 of those, kind of to wrap up and summarize the usefulness of these equations. So the last step, actually, I need to do one more thing. Looking back at that very first equation, I'm going to do something with this one. All of these other equations I see have delta x in them. So I'm going to change this equation here. I'm going to get a red. And I'm going to subtract xi from both sides. Minus xi. xf minus xi, final minus initial position, isn't that just delta x? So I'm going to go ahead and rewrite this whole equation down here a little bit differently for my equation 1. So these are going to be our big three equations of motion that we're going to use as we go through this unit on constant acceleration. Okay, so here's the big three. The first one comes from our position time graph. Delta x is equal to 1/2 a delta t squared plus vi delta t plus xi. Okay. Actually, no, I'm going to take away the xi, just kidding, because now we made it delta x. Okay, so this is our first equation. How is this useful? It relates which terms? First term is delta x, so it relates displacement. Okay. It relates displacement. The second variable in there is acceleration. It relates initial velocity. And it relates time. So if I know three of those four things, this is the equation that I can use to solve for an unknown. All right, let's look at the second equation. Second one we got was from the velocity time graph. Vf equals a delta t plus vi. You may also see this equation written as acceleration is equal to delta v over delta t. It's the same equation, we just rearranged it a little bit. And this is going to relate the variables listed. Relates final velocity. It relates acceleration. It relates time. And it relates initial velocity. So, if you know three of those four, this equation's your go-to. The last equation is the one that we just derived. And that's going to be that one that doesn't have time. So Vf squared equals Vi squared plus 2a delta x. And this one's going to relate my final velocity, my initial velocity, and last but not least, it's going to also relate my acceleration and displacement. So if I have three of these four, I can use this equation to find my unknown. I'm super excited because when we get into some of the later on in this unit, we're going to use these big three equations, but I wanted to make sure I formally defined them for you while they were fresh in your mind, and I hope that this was helpful.